So boron is one that you'll see very often. It's an exception to the octet rule because it usually, not always, but usually makes 3 bonds instead of 4. And beryllium, I believe, usually makes 2 bonds instead of 4.
This is not.
And then the other one that you'll see often, obviously, is hydrogen, and it makes 1 bond.
B usually makes.
All right. Aluminum. So, Josh, when you say it also said aluminum, what do you mean it also said aluminum? The book. Okay. Okay, yeah. And I think for the most part, I'm going to promise it, but I think for the most part, when you run across aluminum, it's going to be in some sort of a, gosh, what are those called? Ionic compound? I don't know why these words just disappeared. Yeah, it says beryllium, boron, and aluminum tend to form electron-deficient molecules. Aluminum normally will form like it's not going to form a molecule because it's a metal. So it'll be some sort of ionic compound. But yeah, you could see something strange there. When you see aluminum kind of bonding to other stuff, that's when you get into structure and bonding, and that's, or inorganic chemistry. You'll get into it there also, and you'll start to learn that the transition metals, there's an 8 electron rule for all the stuff we've been working with, and for transition metals, there's an 18 electron rule, but we're not going to get into that. So, but yeah, there's some strange stuff. But yeah, boron and beryllium and hydrogen will be happy to take less than 8. Yeah, for transition metals, not always, but a lot of times their goal is to kind of build up a complex with 18 electrons. And I say complex because it could still be ionic, but the metal could be in the middle, surrounded by the nonmetals in a way so that it ends up with like 18 connections or something like that, or 9 connections. So, okay. So let's take a look at BEF2. You might see something like this. So fluorine has 7 valence and beryllium has 2. Yeah, the study session is 5 to 7 tomorrow. I think beryllium has 2. Yeah, beryllium has 2. So even though beryllium is a metal, I mean, you can see some things will go like this with beryllium. It is a weird exception. And then there's like BH3, which just looks like this. But when you get finished drawing that, you're like, but boron doesn't have an octet. And then you're like, well, I can't make a double bond with anything. But at this point, boron is just done. So it's good. Does anybody need a second on this page? No? Okay. All right. Somebody be taking notes for Reeb if you guys don't mind, because it looks like his volume is going in and out today. Then we have odd electron molecules. The example they give in the book is NO.
Wait.
And then in this case, nitrogen only has 4 electrons, so you can make a double bond here. And then at that point, nitrogen's got 2, 4, 6, 7. Why didn't boron get 5? I would say that I think it's in group 5, right? Let me check. No, it's in group 3. Okay, so boron has 3 valence electrons around it. Or that's not the right drawing. Boron has 3 valence electrons out around it, so it has 3 places it can bond. And that's just why. All right, so in this one, what would happen if I gave it a triple bond? What goes wrong at that point? The one here. Nitrogen would have 9 electrons, right? So this one, where we see it has an odd number of electrons, is called a radical. And it's an exception to the octet rule. They call them free radicals. And you've probably heard commercials and stuff where they say, you know, if you eat this, it will take care of your free radicals, or drink this, whatever. It's great for free radicals. And you're like, well, good. I don't want any of those. Free radicals tend to be very reactive. So they're kind of like a chain reaction. So this one could react with something else, and then you end up with a molecule that's also a free radical that then reacts with something else to fix this problem, and then you get another free radical. It just keeps going and going and going. So the problem with free radicals is that they just are so reactive. So it's kind of a bit of a chain reaction thing there. But yeah, if you see something that's a free radical, do yourself a favor, though, and go back and recount your electrons to make sure that you didn't accidentally miscount them. And if you count them and you've checked to make sure there's not like a charge or something that you missed, then having a radical that just has 1 electron is perfectly okay. In this bond, yes. Well, no, technically it still has 5 valence, but in this molecule, it only has access to 7 of the electrons. So it has full access to this one, and this one, but it's sharing this and this. So in total, it only has access to 7, but it still just has 5 valence electrons. That's a good question, though, Kevin. Let's see. Hang on just a second. There's something wrong with my screen that's showing most of the chat window, but not all of the chat window. Let's see if I can fix that real quick. Better. Okay. So with an odd number of electrons, do you just give it the most? Yes, you just give it the most that you can get, but don't give it more. Don't give it too many, right? Especially if it's not something that can take an expanded octet. Does anybody remember, it's like the first sentence in the part about the expanded octets. What period is it that they start expanded octets? Correct, period 3 and below. And looking, if you have a periodic table handy, something maybe pulled up in another window, when you get to period 3, you get closer to the D levels, and that's what's causing it to be able to take on more electrons. So it doesn't necessarily, like, in row 3, it's 3s2, and then 3p6, and then you go 4s2, 3d. So the d is sort of out of place, but since they're close to the d orbital, it can take on more electrons than expected because it has more spots to do that. So let's do an example like that. So you can see, like, when do I make it an expanded octet? Any questions about these radicals before I move on? No? Okay. So the way you know you have a radical is you just count up your electrons, and once you've counted them up, they're just an odd number of electrons. Then you know right off there's going to be a radical there somewhere. All right, so let me pull up an example. I'll do the one in the book, and I'll explain kind of how you know. Okay, so there's one set where you would know obviously that it's an expanded octet. So it would be something like PCl5. Phosphorus would be in the middle, and then you'd have 5 chlorine around it. Imagine this chlorine right here. I'll just put it. Those really should be on the top. I just kind of don't have a top there. So everything's got octet, but phosphorus has gone beyond an octet. So one thing you might be tempted to do would be to, like, put a chlorine out next to a chlorine or something, but that's not necessary. So you'll see this. Phosphorus is one of the things that's in group 3 and below. When they say group 3 and below, they're talking about the central atom, not the ones on the outside. And so this, you can tell it goes to an expanded octet just because when you put it together, it forces it to an expanded octet. So those are easy expanded octet questions. They have more difficult ones, like SO4. So you probably saw this one in your textbook, and I just want to explain it. All right, so when you do a Lewis dot structure, you've got to count up the valence electrons first. So sulfur's in group 6, so it has 6 valence. Oxygen's in the same group, which is group 6, so that's 6 valence times the 4 oxygen. So that's 6 times 5 is 30. All right, so we've got sulfur and 4 oxygen. Oh, thanks, Ari. And we've used 8, leaving 22. Ah, shoot. I forgot about the charge. Yes, you're correct, Josh. See, that's what you shouldn't do. You should always make sure you count your electrons correctly. Not like I do. Do like I say, not like I do. SO4 2 minus, it's sulfate. So it's 32 electrons, valence electrons. So you got S, O, 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 O. So basically, you've got sulfur is 6, oxygen is 6 times 4, and then you've got this 2 minus, so you got to add 2 more electrons to it, and that's a total of 32. Okay. And so we've used 8. That leaves 24. And at this point, we've followed all our rules. We've used all our electrons, and everything has an octet. So normally, we would say, done. But we've got to go one step further because this is one that might have an expanded octet because of the period that it's in. When I say period, periods are the horizontal rows in the periodic table, And then the groups are the vertical columns. The groups are also called families as well. So let's calculate the formal charge of sulfur. So sulfur has 6 valence electrons, and it has no lone pair electrons, has 4 bonds, so 6 minus 4 is plus 2. And then all 4 oxygens are identical. I'm glad, Umar. Oh man, I said that they needed to be taking notes for Arib. I meant Umar. What about that, Arib? Yours is working fine. Okay, so oxygen has 6 also. It has 6 lone pair electrons and 1 bond. So that's minus 1. So it's plus 2, minus 1, minus 1, minus 1, minus 1. Do those look like really good formal charges? Yes, that's what I mean. 3, 4, 5, and below. Yeah, these are bad formal charges. Now, if this was the best we could get, we'd be like, all right, I'll take it. But we can do better than this. How can we do better than this? Double bonds, right? Yeah, correct. So it's got a minus 2 charge. So we've got minus 1 plus minus 1 plus minus 1 plus minus 1 plus positive 2. And so overall, that ends up equaling minus 2. And that's correct because we have a minus 2 charge. Right? You can make a double bond. That is correct. And Jason, that's correct too. So that's what we're going to do. I'm going to make a double bond here. Get rid of these electrons. And so that's going to change this formal charge. What is the formal charge going to change to there? It's 6 minus the lone pairs minus the bonds. Correct. That's going to go to 0. I'm going to put the new ones in purple. So the ones we've adjusted. So now we've got minus 1 plus minus 1 plus minus 1 plus 2. What does that equal when I add them all up together? Minus 1. That's bad, right? Why is that bad? And I'll answer you in 1 second, Kevin. What's it supposed to add up to be? The charge, right? And the charge is minus 2. So it's adding up to be minus 1, not minus 2. So that's not good. But if we look at this too, it also changed the formal charge on the sulfur. All right, so now I'm going to answer Kevin's question. He said, why did we make a double bond? And that's a good question. It's because we want to decrease the formal charges. And if we can decrease the formal charges at all, we've done a really good job. The reason we can add a double bond here, but in other places we can't, is because sulfur is in the 3rd period or below. Right? So everything in the 3rd period and below can have more than 8 electrons. It doesn't mean it always does. It just means that it can. Does that make sense, Kevin? Yep, cool. All right, so we're going to do the formal charge on sulfur. Now it's changed. So sulfur is 6. We've got no lone pairs. We've got 5 bonds. So now it's plus 1. So now if we add them all up together, we do get a minus 2 charge. No, it doesn't matter which oxygen. We could do any oxygen we wanted. So can I do better than these formal charges? Yes, I can do better. I'm going to make another double bond. I'm going to make it on the opposite side. The reason I'm choosing the opposite side is things tend to happen like in an even manner. because if you put not lone pairs, if you put two double bonds together, there's a lot of electron density there, and they're going to repel each other.
Okay.
So instead, I'm going to put it on the opposite side because that'll be a lot more even, and that'll work out better. All right, so I'm going to put my double bond there, and then get rid of the lone pairs I borrowed to do that. All right, so I'm going to erase this right here because the sulfur changed again, right? And the oxygen is different. Now I'm going to put them in orange because I've made a third change. So what the oxygen on the left looks just like the oxygen on the right. So should I recalculate the formal charge for oxygen? No. Correct. Because it looks the same. It's going to be the exact same calculation. It's going to be 6 minus 4 lone pair electrons minus 2 bonds, right? Now, what happens if when we calculate sulfur? We have sulfur minus no lone pair electrons minus 6 bonds. What is that? 0. All right. So at that point, if we want to check and see, like, what if we made a third lone pair? I mean, not lone pair, third double bond. So we'll do that. It would be wrong, but I'll show you why it's wrong. So I will erase this. And then let me pick another color. We'll do it in green, I guess. All right. So in this case, oxygen is 0, which is good. And sulfur, oh, don't do it. Oh, crud, it's the wrong button. Shoot. Sorry, guys. I'm having a little tantrum. Okay. So sulfur, oxygen, oxygen, oxygen. And then we were going to do a double bond oxygen down here. This should be 2 dots, not 1. And then, so that was 0, 0, minus 1, 0. And we were just about to calculate sulfur. What is sulfur's now? Minus, yeah, plus, is it plus 1? I think you're probably right. Minus 1. All right, so it's 6 minus 1, 2, 3, 4, 5, 6, 7 equals minus 1. So here again, we have minus 1 and minus 1. Why is this worse than the other one? The other one looked like this. And we had minus 1 and minus 1. Correct. That is correct. Because oxygen is more electronegative, so it should get the negative charge, not sulfur, right? So if it's on sulfur, that's not good. We broke one of our own rules. So that was the problem there. So if we look at the periodic table, we've got oxygen on top. I think sulfur is right below it. And then you've got some other stuff in group 6. So as you go down a column on the periodic table, does it get more or less electronegative? Less. Correct, because the deal with electronegativity is as you go up and as you go to the right, it gets more electronegative until you hit fluorine, which is the most electronegative atom. All right? Okay, let's see how much time we've got. We've got 8 minutes left. Explain what each number in the formal charge represents again. Sure. All right. So, do you mean on this particular problem or formal charge in general, Jennifer? In general, okay. I'm going to delete this. Let's try carbon dioxide, but not in red. Let's do it in blue. All right, so formal charge is equal to the valence electrons minus the combination of lone pair electrons plus the bonds. Right. So looking at carbon, carbon has 4 valence electrons. It has 0 lone pair electrons on the carbon. It has 4 bonds. So 4 minus 4 is 0. So carbon is 0. So now let's take a look at the oxygen. Both of the oxygen have the same number of bonds and the same lone pair electrons, so we really only have to calculate it once. Yes, you will be allowed to use scratch paper on the test. All right, so with oxygen, so this was carbon, this is oxygen. Oxygen had 6 valence electrons minus, it has 4 lone pair electrons, 1, 2, 3, 4, plus the 2 bonds here and here. So that's 6 minus 6 equals 0. So that's 0, and that's 0. So the goal with the formal charges is to get them as low as you can and make sure they equal the charge of the molecule. So if the molecule is like a polyatomic ion, then they have to equal the charge of the polyatomic ion. Like SO4 2 minus had to equal had to equal 2 minus. Yeah, when sulfur, yeah, let me draw the best example of that. Does anybody need a second on this page before I go back to the sulfur? Nope, okay. All right, so for the sulfur one, it was, this is the best structure. All right, and then since it's a polyatomic ion, and I didn't do this on the last page, but I should have, you put it in brackets and put the charge out here. And it doesn't matter if I chose to put the double bond on these 2 oxygen, or if I chose to do the double bond on these 2 oxygen. Right? Could have done either way. It doesn't really matter. As a matter of fact, there's resonance in this one because I can draw it the other way. And so that is going to be a resonance structure, which would look like this. With my double-headed arrow. Normally the double-headed arrows are a little bit longer, but I don't have any space. All right, so if I have more resonance, does it make it more stable or less stable? Try the opposite. Go the other way. More stable. Yeah, so more resonance makes it more stable. How and why? I was actually just wondering that. I'm going to look that up. I have known the answer to that, but I don't know it at the moment. So, yeah, you got me on that one. Like, your guess is as good as mine, but that's probably a bad teacher answer. So, I will look that one up. Yes, it would be wrong if you don't minimize the formal charges as close to 0 as possible. The reason is because now that you know that things in the 3rd period and below can have an expanded octet, then you would know that it's okay to try to minimize the formal charges by making double bonds if you can. Does that make sense, Tiana? If you have spare time, go ahead and do 4C. If you don't have spare time, wait until I get back with you tomorrow, and I'll let you know whether or not you have to do 4C. Okay, which question was it? Yes, that's correct, Braylon. All right, which question was it?
So you want to try
The electronegativity chart won't be, but if you need to know the electronegativity numbers, like if I say, what's the electronegativity difference between carbon and oxygen, and I want a number, you'll be given the electronegativity of carbon and the electronegativity of whatever other atom I just said. I think it was oxygen. So, structure for SF3CN. Okay. All right. What if it's like the bond is more polar? It's possible you might not even need the chart. So if you don't have the chart and I say which is more polar, the bond between carbon and nitrogen or the carbon-hydrogen bond, then you kind of look at where they are on the periodic table. There's like carbon and then nitrogen are right next to each other. And then hydrogen's over here. Things that are really close to each other on the periodic table have lower electronegativity differences. So the bond between carbon and nitrogen would be lower than the bond between carbon and hydrogen. All right. So with sulfur, we've got 6 valence electrons. Fluorine is 7 times 3 is 21. Yes, greater distance, more polar. And then carbon is 4 and nitrogen is 5. So that would be what, 36? So we've used 2, 4, 6, 8, 10. And knowing that the carbon goes next to the nitrogen is, I know that because I've done this for a long time, but since you guys are new to this, you might not know that the carbon and the nitrogen are supposed to go together. So, yes, it's going to be a multiple bond there. So we got 26. So we do the regular thing here, right? And we've used 18. So, gosh, what does that leave? 8. All right. So now the question is, do I want to fill them in on carbon or do I want to fill them in on nitrogen? Doesn't really matter much because you can pull lone pairs from either one if you need to. But nitrogen is more electronegative. So I'm going to assign most of them to nitrogen and then whatever's left over I'll put on carbon. Okay, so that's all 8. So then I want to check to see if everything has an octet, and everything here does, except for carbon. Carbon does not. So I don't have anything on sulfur that I can pull down to make a double bond. If I make a double bond with this lone pair, it's not going to change anything because carbon already has access to those. It needs access to some that it doesn't have. So what I'm going to do instead is I'm going to borrow the ones at the bottom, or I could take the ones at the top or the side, doesn't really matter. And we make a double bond here. All right, now everything has an octet. So at this point, I want to check all of the formal charges and make sure that that's as low as we have. All right, so fluorine is 7 minus 7 is 0. 0, 0. Carbon is 4 minus 1, 2, 3, 4, 5. So that's minus 1. Nitrogen is 5 minus 1, 2, 3, 4, 5, 6. So that's what? Minus 1. And then sulfur would be plus 2. So that's a bit odd, right? So probably what I would do at this point to lower the formal charge would be give it a double bond here at that point. Yeah, it does make it neutral, but we do want them to be as low as possible. Spencer, you have a question.
So on the homework I was having issue. Can you hear me?
Yeah.
On the homework I was having issue. I ended up getting a lot of questions wrong, mostly because I couldn't put it in correctly. I didn't know if it was on my part or on SmartWorks' part, but I wanted to just double check the process at which, because you just did it, but I'm just wanting to double check that you put each of the molecules in the correct structural format. You give them each one bond, then you the additional electrons that they're missing with lone pair electrons on the outside, and then you do so on the inside. And
Yes.
I just, because the first thing I think of when I see sulfur, carbon, nitrogen is just double bonds for going out of the carbon, because 4 hydrogen and 1 carbon is 1 for each hydrogen.
Yeah.
So I'm filling it out of order because there should be a process to this. But I'm just trying to figure out exactly.
Yeah, no, that's correct. That's actually the right process. And it's also really, really uncommon to see lone pairs on carbon.
Okay, it just didn't seem right. That's what I asked.
Yeah.
Well, and then I guess one specifically, and you just went over it, I think, but nitrogen typically because when I was looking in the book, there's